Modern microscopes can reveal details up to 1,000 times smaller than a grain of salt, including viruses and countless other fascinating structures invisible to the unaided eye. This remarkable tool allows scientists to explore the tiniest forms of matter by producing highly magnified images that bring their features into focus. In this video, we'll explore 16 incredible things discovered through the lens of a microscope. Let's start with something that often bothers people: mosquitoes. But wait until you see what's really happening when one of these tiny insects decides to make you their next meal. When observed under a microscope, a mosquito's head reveals some surprising details. That slender proboscis isn't just a single needle. Inside the sheath are actually 6 specialized parts, each with its own role. 2 have tiny serrated edges that can slice into skin so precisely you may hardly notice the bite. It's a design as delicate as surgical equipment, but adapted for feeding on blood. The other components work in coordination. 2 help keep the skin slightly parted while the mosquito feeds, while others sense the natural chemical signals released by blood vessels, guiding the insect to its best source of blood. As the mosquito's abdomen fills, it expels excess water from the blood to make room for more concentrated nutrients, particularly red blood cells. The itching that follows is not from the bite itself, but from your body's immune response to proteins in the mosquito's saliva, which are injected to prevent clotting and keep the blood flowing. In some regions, mosquitoes can also transmit viruses and parasites, which is why they are considered significant carriers of disease. Sharks are among the ocean's most remarkable predators, and while their rows of sharp teeth often capture attention, their skin is just as fascinating when examined under a microscope. If you've ever touched shark skin, you'll know it feels like sandpaper, but on a microscopic level, the structure is even more extraordinary. Shark skin isn't smooth like human skin. Instead, it's covered with dermal denticles, also called placoid scales, which are tiny tooth-like structures. These denticles are made of dentin and enamel, the same materials as teeth, and they're arranged across the shark's body in overlapping patterns. The design of these denticles serves 2 important purposes. First, they reduce drag by streamlining water flow, giving sharks a hydrodynamic advantage and enabling them to swim with remarkable speed and efficiency. Second, their tough, armor-like texture helps protect sharks from injury and parasites. As sharks move, the ridges on the denticles create small swirls in the water, reducing turbulence and allowing smoother, faster motion. And just like the teeth in their mouths, sharks can replace damaged denticles, ensuring their skin remains an effective combination of protection and performance. That soft, golden sand beneath your feet may look simple, but under a microscope it reveals an incredible story of Earth's natural history. Sand isn't just made of broken rocks. In many places, especially tropical beaches such as those in the Caribbean, it consists largely of biological material. Much of this sand is formed from the skeletal fragments of corals, tiny shells made of calcium carbonate, and the remains of countless marine organisms that once lived in reef ecosystems. Even parrotfish contribute by grinding coral while feeding and excreting the fine grains that eventually become part of the beach. Viewed up close, each grain of sand shows remarkable variety: pieces of coral that once sheltered polyps, fragments of shells, and mineral particles shaped by waves and time. What seems uniform to the naked eye is actually a diverse mixture of geological and biological material. Sand also varies depending on location. Desert sand is primarily composed of wind-worn quartz grains, though many deserts were once seabeds long ago. Volcanic bacas, such as those in Hawaii or Iceland, often contain dark basalt fragments created from cooled lava. Each type of sand carries clues to its unique origin. Now that you know what sand is really made of, which type of sand fascinates you the most? Coral-based tropical sand, quartz-rich desert sand, or volcanic black sand? Let us know in the comments below. Peacock feathers look beautiful to the naked eye, but under a microscope, they reveal a remarkably intricate structure that seems almost too precise to be natural. The iridescent colors aren't created by pigments as you might expect. They arise from a microscopic architecture that manipulates light through structural coloration. Each feather is made of barbs and barbules, which contain a highly ordered arrangement of melanin rods and air gaps embedded in keratin. These nanostructures have dimensions on the scale of visible light wavelengths, roughly 150 to 200 nanometers, functioning like natural photonic crystals that reflect specific wavelengths through constructive interference. At high magnification, the arrangement appears so precise that it resembles engineered nanotechnology. The number of layers, the spacing of the rods, and the thickness of keratin all vary slightly across regions of the feather, producing shifts in color with mathematical consistency. One striking demonstration of this phenomenon is that when the air spaces in the nanostructure are artificially filled with substances such as glycerin, the vivid colors disappear. This proves that the visual effect comes from the feather's nanostructure rather than pigments. In essence, peacock feathers showcase that nature has been applying advanced principles of optical engineering for millions of years. Those bright yellow flowers in your yard hold a fascinating microscopic secret that highlights nature's clever reproductive strategy. What looks like a single blossom is actually a composite of many tiny individual flowers grouped, which helps explain why dandelions are so successful at spreading. Under magnification, a dandelion reveals itself as a highly efficient reproductive system. The yellow petals are actually florets, and each floret contains its own reproductive parts. After pollination, seeds begin to develop at the base, each attached to a fine tuft of white fibers that will eventually form the familiar spherical seed head. One especially interesting detail is the stigma at the top of each floret. Under a microscope, it appears with lobes covered in pollen grains, perfectly adapted to catch pollen and ensure reproductive success. The entire flower head functions as a collective unit, with every floret contributing to seed production. When the yellow flower transitions into the white seed ball, the microscopic design is equally remarkable. Each seed, called an achene, is attached to a parachute-like structure known as a pappus, which allows it to travel long distances on the wind. This adaptation ensures dandelions can colonize new areas efficiently. And before we continue unfolding this fascinating discovery, be sure to subscribe and hit the bell so you don't miss any future episodes. Don't forget to share it with your friends too. It helps the channel out, and I'm excited to continue bringing you more awesome content. Snow looks pure and beautiful when it blankets the landscape, but under a microscope it reveals structures so intricate and varied that they seem almost otherworldly. What most people know about snowflakes barely begins to describe their microscopic complexity. Each snowflake forms when water vapor in clouds condenses directly into ice crystals around tiny particles such as dust or pollen. Under magnification, these crystals display an astonishing range of shapes influenced by temperature, humidity, and atmospheric conditions. No two fully developed snowflakes are indeed exactly alike. Many follow the classic six-sided symmetry, but they can also appear as thin plates, hollow columns, needles, dendrites with delicate branches, or other geometric forms. Their diversity arises from the constantly changing conditions they encounter as they fall through the atmosphere. Researchers can sometimes infer the conditions in which snow formed, such as temperature and humidity, based on crystal shape and structure. However, it is not possible to identify the exact geographic location where snow fell solely from electron microscope images. On Earth, snow is composed only of frozen water. By contrast, at the poles of Mars, scientists have detected carbon dioxide snowflakes, sometimes called dry ice snow, in addition to water ice. And these form very different structures due to their composition. Each snow crystal is a product of precise atmospheric physics, where temperature and humidity guide its growth into intricate, symmetrical patterns. The result is natural beauty shaped by physical laws, not design. That white stick, once common in classrooms, carries within it the microscopic remains of organisms that lived tens of millions of years ago. Chalk isn't just a simple mineral. It's a type of limestone composed almost entirely of the skeletal remains of tiny marine organisms. Under a microscope, chalk reveals its biological origin. It is largely made up of the calcite shells of coccolithophores, single-celled algae that thrived in Earth's oceans during the late Cretaceous period, around 99 to 66 million years ago. When these organisms died, their shells settled on the seafloor, gradually accumulating in thick layers. Over time, the pressure of overlying deposits compacted these layers into chalk. What you see under magnification are the preserved microscopic shells and skeletal structures of these long-extinct organisms. It's essentially a fossil record on a microscopic scale, where the remains are still individually recognizable. Every time chalk is used, the fine white dust is made up of these ancient calcite remains, not just inert mineral powder, but the compressed legacy of life that existed in the oceans long before humans appeared. Chalk is distinct among limestone formations because its biological origins are so clearly visible. Unlike other limestones formed from mixed sediments, chalk preserves the direct evidence of countless coccolithophores compacted together over millions of years to create the material we still use today. At first glance, your skin may seem smooth and uniform, but under a microscope it transforms into a highly detailed landscape full of intricate structures. Looking closely at its layers reveals why human skin is such a remarkable protective and sensory organ. The skin is not a simple surface barrier. It consists of multiple layers, with the epidermis on top, composed of the stratum basale, stratum spinosum, stratum granulosum, and the outer stratum corneum made of keratinized cells. Beneath the epidermis lies the dermis, containing connective tissue, sweat glands, hair follicles, nerves, and blood vessels. Fingerprints, which appear as raised ridges to the naked eye, are actually complex ridge patterns containing sweat pores and fine textures that help secrete oils and salts. Under magnification, these ridges resemble peaks and valleys dotted with pores that connect to underlying sweat glands. Advanced imaging has shown that fingerprint patterns extend below the surface of the skin. The ridges are not just superficial marks, they are three-dimensional structures formed by underlying dermal papillae and sweat ducts that shape the surface patterns. Research has also shown that the spacing of fingerprint ridges plays a functional role. They help enhance tactile sensitivity by amplifying vibrations when you touch a surface, improving your ability to detect texture. This means fingerprints serve not only as unique identification markers but also as built-in sensory enhancers within your skin. Have you ever compared your fingerprints with someone else in your family? Were they very different? Let us know in the comments below. If you thought tapeworms were disgusting before, wait until you see what their heads look like under a microscope. Tapeworms are ribbon-like parasitic worms made up of segments called proglottids, which contain eggs and are continuously released to infect other organisms. Several species can infect humans through undercooked pork, beef, or fish, but it's their microscopic head structure that reveals the true horror of these parasites. The tapeworm head, called the scolex, looks like something designed by a sadistic alien intelligence. Under magnification, you can see suckers and, in some species, hooks that look like medieval torture devices. These aren't just simple attachment points. They're sophisticated biological anchoring systems designed to latch onto your intestinal wall with a grip so strong, it's almost impossible to remove. The hooks, present only in some species, such as Taeniosolium, are curved and sharp, designed to dig into your intestinal tissue. The suckers work like biological vacuum cups, creating negative pressure that helps secure the worm's position. Once a tapeworm finds the ideal location in your digestive tract, it uses these structures to anchor itself so securely that it can feed on your nutrients for years without being dislodged. What makes this even more disturbing is that tapeworms don't have mouths. They don't need them because they simply absorb nutrients directly through their body surface. The head exists solely to maintain its parasitic grip on your internal organs while they steal your nutrition and reproduce inside your body. The next time you're swimming in the ocean and accidentally swallow some seawater, remember what I'm about to tell you. That seemingly clear blue water is actually teeming with microscopic life forms that transform the ocean into a living soup of creatures you never knew existed. Beyond the salt and minerals you'd expect, seawater contains an incredible diversity of microscopic organisms. Under a microscope, every drop reveals free-swimming bacteria, phytoplankton, including diatoms and dinoflagellates, and countless other microbial species that are completely invisible to the naked eye. What's truly unsettling is the sheer number and variety of organisms living in every sample of seawater. You'll find algae, protozoa, fish, eggs and larvae, copepods, rotifers, microscopic worms, and many different bacterial species. A cast of characters that looks like it belongs in a science fiction movie rather than in the water you swim in. The most disturbing part is realizing that this microscopic ecosystem exists in every part of the ocean. Whether you're swimming in tropical waters or cold northern seas, you're surrounded by and ingesting countless microscopic organisms with every breath and every accidental mouthful of water. These organisms aren't just passive inhabitants, they're actively living, reproducing, and dying in the water around you. Some are beneficial, some are neutral, and others can cause illness or infection if they enter your body in sufficient quantities. The fabric fibers in your clothes reveal striking differences when viewed under magnification, and understanding these differences will change how you think about everything you wear. Natural fibers like cotton show a ribbon-like, twisted form with convolutions in a central hollow channel called a lumen. Under moderate magnification, cotton fibers look almost organic and alive, with their twisted, rope-like structure. Linen fibers appear smooth and polygonal, exhibiting nodes or joints along their length that resemble bamboo segments. These natural breakpoints make linen both strong and flexible, but under a microscope, they create an almost mechanical appearance that seems engineered rather than grown. Animal fibers reveal even more striking details. Wool displays a scaly surface called the cuticle, with some types also containing a medulla or central core that creates irregular internal contrast. Under magnification, wool looks like it's covered in overlapping scales, similar to snake skin or fish scales, giving it an almost reptilian appearance. Silk fibers appear deceptively smooth and featureless in longitudinal view, but their cross-sections reveal triangular or rounded shapes that give silk its characteristic luster. The uniformity is almost unsettling in its perfection. Synthetic fibers present their own microscopic peculiarities. They show very uniform diameters and smooth surfaces with consistent cross-sections that are often circular or engineered into lobed shapes. The artificial perfection of synthetic fibers under a microscope makes them look more like manufactured products than textile materials, which is exactly what they are. Here's something that will make your skin crawl, literally. Mites are living in your home right now, and when you see what they look like under a microscope, you'll understand why they're one of the most common causes of allergies. More than 48,000 species of mites have been described, but scientists estimate there may be hundreds of thousands to over 1 million species in existence. They're found almost everywhere, in soil, on plants, in caves, in fresh water, and throughout your home. The most common household variety, dust mites, thrive in warm, humid environments and feed on something particularly unpleasant: the flakes of skin that humans naturally shed every day. Under a microscope, mites reveal their true arachnid nature. Their bodies aren't divided into a distinct head, thorax, and abdomen like insects. Instead, the front section contains specialized mouthparts used to pierce, scrape, or suck, depending on the species. Dust mites don't bite humans, but they do use these structures to feed on skin particles. They lack eyes and a brain in the traditional sense, functioning instead as simple, highly adapted feeding and reproducing machines. What makes this truly disturbing is the scale of mite presence in the average home. Large populations can thrive in mattresses, carpets, and upholstered furniture. A single mattress can contain hundreds of thousands to millions of dust mites, all feeding on dead skin cells and producing waste products that trigger asthma and allergic reactions. The proteins in mite feces and body fragments are what cause allergic reactions in sensitive individuals. So when you're reacting to dust mites, you're actually reacting to microscopic arachnid debris floating in the air you breathe. After hearing that a single mattress can hold hundreds of thousands of dust mites feeding on shed skin cells, how does that fact make you feel about where you sleep tonight? Let us know in the comments below, and don't forget to subscribe and follow the channel to discover more interesting things. Velcro might seem like a simple modern invention, but its microscopic structure reveals a fascinating and slightly unsettling story of biomimicry. When examined under magnification, Velcro shows exactly how humans learned to replicate one of nature's most effective attachment mechanisms. The hook and loop fastener system consists of two distinct parts that look almost organic under a microscope. The hook section contains thousands of tiny curved hooks that resemble microscopic fishing hooks or claws. The loop section is made up of countless small fabric loops that appear like tiny lassos waiting to be caught. When these two surfaces are pressed together, hundreds or thousands of individual hooks catch in the loops, creating a secure attachment through sheer numbers rather than individual strength. Under magnification, you can see exactly how each hook grabs multiple loops, creating a complex interlocking system. What makes this particularly interesting is that Velcro was invented in 1941 by Swiss engineer George de Mestral, who studied how burrs from the burdock plant clung to his clothing and his dog's fur. When he examined the burrs under a microscope, he discovered they were covered in tiny hooks that latched onto loops in fabric fibers. This means that every time you use Velcro, you're using a human-engineered version of a plant's natural dispersal strategy. The microscopic reality of coronavirus particles on masks reveals details that many people find surprising and somewhat disturbing. SARS-CoV-2 virions are about 60 to 140 nanometers in diameter, far smaller than the micrometer-sized fibers in common fabrics, yet they can still be trapped within the dense fiber networks of masks. Under electron microscopy, researchers can observe how these tiny particles cluster and adhere to mask fibers through multiple mechanisms, including electrostatic attraction, inertial impaction, interception, and diffusion. What looks like plain fabric to the naked eye is actually a complex three-dimensional micro-landscape capable of capturing microscopic threats. N95 respirators contain finer, more tightly packed fibers than surgical or cloth masks, creating smaller pores that improve filtration efficiency. Under magnification, the difference between mask types becomes dramatically apparent. High-quality respirators show dense, maze-like fiber networks that create multiple opportunities to trap particles. The most unsettling aspect is seeing virus-like particles adhered to mask fibers in electron microscope images. These clusters demonstrate that capture occurs not by simple sieving, but through complex physical and electrostatic interactions between the virus and the mask material. Music technology has advanced significantly, but the microscopic reality of vinyl records reveals an analog recording method that seems almost magical when viewed under magnification. These records, made from polyvinyl chloride, contain sound waves that are literally imprinted into their surface as physical grooves. Under a microscope, the complexity of vinyl record grooves becomes astounding. What appears as simple spiral tracks to the naked eye reveals itself as an incredibly detailed landscape of ridges and undulations that correspond to the original audio signal. The analog nature of vinyl means that every nuance of the original recording is encoded as continuous variations in the groove walls. Under high magnification, you can see how louder sounds are represented by larger side-to-side groove modulations, while softer sounds produce smaller variations. High-frequency sounds appear as rapid, fine oscillations, while low-frequency sounds create broader, more widely spaced patterns. What's truly remarkable is that a simple stylus following these microscopic grooves can recreate the original sound with stunning accuracy. The physical relationship between groove modulations and the resulting vibrations is so direct that many audiophiles believe vinyl provides superior sound quality to digital formats. The stylus must track grooves that are only a few micrometers wide while maintaining perfect contact to reproduce the original audio signal. Our final revelation involves something you probably have in your refrigerator right now. Orange juice might appear to be a smooth, simple liquid, but under a microscope it reveals a complex mixture of suspended particles, crystals, and droplets that looks more like a miniature landscape than a breakfast beverage. Orange juice contains numerous compounds, including vitamin C, sugars, carbohydrates, potassium, thiamine, folate, and citric acid. When concentrated or dried on a slide and magnified, these components can form crystalline patterns that resemble geological formations rather than something you drink. Under polarized light microscopy, different compounds in orange juice display a variety of colors, creating a kaleidoscope effect that highlights the hidden complexity of this seemingly simple liquid. The sugar crystals, acid salts, and other molecular structures all have distinct microscopic appearances. What's particularly surprising is that both smooth and pulpy versions of orange juice show similar complexity under magnification. Even juice that appears completely smooth to the naked eye contains countless microscopic particles, droplets, and structural elements that make up its internal landscape. The next time you take a sip of orange juice, remember that you're drinking a liquid containing thousands of different microscopic structures, each with its own shape and chemical composition. What seems like a simple beverage is actually an incredibly complex mixture of organic compounds, all visible and distinguishable under proper magnification. Which of these microscopic revelations shocked you the most? Have you ever looked at everyday objects under a microscope and discovered something surprising? Share your thoughts in the comments below. If you enjoyed today's video, please give it a like and don't forget to subscribe to the channel. Your support means a lot to us. Thank you so much for watching, and we'll see you in the next video. Thanks for being with us. Leave a comment, like to show your support, and remember to hit that subscribe button for more exciting videos. See you next time.